All right, this lesson follows what we were doing right before we left. We were talking about one proportion intervals and one proportion tests, and then we went on to talk about the error that happens with those. Now, I had mentioned there were lots of different tests and confidence intervals. So there's one more that involves proportions. As you can see from the goal here, it says be able to find a confidence interval for the difference of proportions using a two proportion z interval. So what we were doing before was what was called a one proportion z interval. They only gave us one sample and then asked us to use that one sample to find the true value in the population with a certain level of confidence. This is a little different because what they'll do is they'll give us two samples, and we're looking for what the true difference between the samples is. So let me talk you through some examples, and then I'll show you how to perform one. So this one will make a confidence interval like we've done before, but it'll make a confidence interval for what the difference is between the actual population numbers using the sample numbers. So, so here's an example. The top says, are men more likely to die on the job than women? And if so, how much? Now, in order to know this for sure, we'd have to take a census. But say we can't take a census, we'll take a sample. Now, it's probably not too surprising to believe that men are actually way more likely to die on the job. Men in general tend to take more risky jobs. You know, they go underwater and weld, or they go out in the space, and not to say women don't get some dangerous jobs, but for whatever reason, men are way more likely to die on the job. And this sample shows that. So the sample comes out 94% of men, of those who die, 94% are men and 6% are women. Now, if this is a sample, it doesn't mean that those are exact numbers, but this seems to be pretty significant. It's not hard to believe that in the true population, even if the numbers are a little off, men seem to die somewhere in the 90% and women are dying at under 10%. So there seems to be a statistically significant difference. Now, sometimes the numbers aren't so obvious. I think we look at that and it's probably agreeable that men are more likely to die on the job from the sample numbers. Right under that, it asks, are graduation rates better now than 10 years ago? And if so, how much? So in order to find that, there were two samples taken, one for 2005, which had the graduation rate at 77%, and then 10 years later, the sample showed 80%. Now, this one's less cut and dry than the other one. It would seem that with the men and women, natural variation probably wasn't enough to account for such a great difference. But now that it's 10 years later, the graduation rate's only gone up 3%. Now, that may or may not be significant, but the difference is a lot less. The difference between the men and the women in the sample was about 88%. Now, that may not be the true difference, but it'd probably be close. Now, the difference between the graduation rate of 2015 and 2005 is 3%. Now, there is a difference in the sample, but once again, is there an actual difference in the population? This could just be natural variation for all we know. It's hard to know about more information about the samples, but this one's a little less cut and dry. If you're the principal, you might want to brag, hey, our graduation rate went up 3%, but once again, due to natural variation, maybe nothing has changed, and we just got a little lucky in 2015 to get one that was a little higher, and basically the graduation rate in general is the same because nothing's really changed. Maybe you just got a little lucky with a better group of kids or something like that. So basically what this procedure is going to do is it's going to allow us to make a confidence interval for what the true difference is. So between men and women in the sample, it was an 88% difference. We can make an actual confidence interval to cover, based on that 88%, what is likely to be the true value. And once again, the true value is likely to be close to 88 within a certain range, and we're unlikely to go beyond a certain range. And same thing for, I'm going to do an example that's different from these, But once again, we could do it for the graduation rates. We could basically go, well, they're 3%, but could we make a confidence interval for their true difference? Maybe the difference really is 4%, or maybe it's 2%, or maybe it's -1 or something. Can we come up with a range that we think has the true difference in it? So even though we have the sample differences, we want, what would the population difference possibly be? And we can make a confidence interval for that within a certain percent confidence, like we talked about before. All right, so that's the idea of what's happening. So to do this, here's the recall. It says since sample proportions under the correct conditions are approximately normal, the difference of the proportions also comes out approximately normal. This occurred when we were doing like the Walmart example, where there were 2 trips, one to Vestal and one to JC Walmart, you might recall. And even if we added or subtracted those trips, even when we added and subtracted them, the new distribution was also normal. So we can use that concept here and go, well, if we had one proportion, we were able to make a normal curve. The difference of the 2 proportions also comes out normal. So that's the concept here, that's even under a difference, so long as the conditions are met, we're getting a normal curve. So to use a normal distribution, we need the mean and we need the standard deviation. That way we can make the curve and then analyze it. So this shows what our mean and standard deviation will be. So since you have 2 proportions, we usually assume when we subtract, the mean's going to be the difference between the 2. So when we go to make our normal curve, the mean that we'll use will be the difference of the proportions. Our sample difference is going to be the average that we'll use. It'll be the center of our curve. Now it says make P1 greater than P2. You don't have to do this, but it just makes sense. If you subtract a smaller number from a bigger number, you don't get a negative. Now, if you reverse them, you get a negative number and you can still work with it. But it makes more sense to take the greater proportion, subtract the lesser proportion, and keep your mean positive. So I'm just putting P1 minus P2, where P1's bigger, so we'll get a mean that's positive. So that will be the mean difference. So if I was doing like the men and the women, I'd put the men first because I would take that higher 90, I think it was 96, I'd have to go back, where the 96 minus the, or 94, I think, 94 minus the 94 minus the 6%, that would make more sense because you'd get a positive 88. Now, if we were doing the graduation rates, I'd use the 2015 number, 80% minus the 77%, and get that the mean difference was 3%. Now, once you have that, that's your point estimate, the center of your confidence interval. In order to make the confidence interval, you also need the standard deviation, or what I'll give you is the standard error, but here it shows standard deviation. This formula that you see is what you use. Now, this is given to you on the exam, but I'd make sure you know how to use it. It's basically the standard deviation for how the differences will come out. So if you were to keep taking sample sizes, and you'll see the sample size in the example, if you keep taking sample sizes of the same type, this will give you how spread out you should be from that mean. So notice that it has P1 and Q1 and N1. So you basically need that P1 number, that's a success, subtract the P1 from 1 and get the Q, and then the N will be given to you in the problem. Do that for the first group, and then do it again for the second group and take the square root of the whole thing. So you have to put a lot of stuff in the calculator, but if you put that all in, and it helps in the calculator to use the fraction entry, the alpha F1, where you can put in a fraction to enter all this so you do it correctly. But basically, if you throw that all in, it'll give you the standard deviation. Now, since we don't know, for our confidence interval, we don't actually know the actual proportions, P1 and P2. Remember, we're using samples. So for what we're going to make the confidence interval, our sample is going to be the difference of the mean, the mean is going to be the difference of our sample proportions. So it's got the little hats on it. and then the standard error is going to use the hats as well. So the top one was if we actually knew the population values. Since we don't know the population values, we're going to use our sample values and create a confidence interval for the actual difference in the population. All right. So this says when making one of these differences of proportions, confidence intervals, we need to be able to use a normal curve. Obviously, the normal curve can only be used if the classic conditions are met. So the conditions are all the same with slight modifications. So there needs to be the independence condition. This needs to be met for each individual proportion. So if I was doing like the men and the women, all the men would have to be independent, all the women would have to be independent, and the men and women would have to be independent of each other. Same thing if it was the graduation rates. 1 year would have to be independent from the other, and everybody within 1 year would have to be independent from each other. The randomness condition has to be met. Both samples have to be picked randomly. The 10% condition has to be met, once again, for both groups. And the success-fail condition has to be met, once again, for both groups. So for these, normally we'd show them. I'm going to talk through them because they take a while to write out. But you have to check to make sure these have been met. If these aren't met, or at least in some way fudge through them, then you can't use the normal distribution, and then you can't do the procedure. We like to do the procedure, so we try to get these met if we can, or just assume that they're met if it's we're not sure if someone did it randomly. We'll just trust them. Once we have all this information, we can make the confidence interval for the two proportions, meaning we can make an interval that gives us what we think the true difference is in the population. We have a sample of each. We know what the difference is between the samples, but we're looking for the true value in the population. Notice the structure of the confidence interval is the same as before. We need a center. We need that mean. The mean is the subtraction of the two. So whatever the difference is in the proportions that of our samples is our center for our confidence interval. Once we know that that's the center, we want to build out, because that's our sample difference, but it may not be the true difference. The true difference should be nearby. So we build a confidence interval using Z star. Remember, Z star can be calculated if you don't know what it is. But usually they'll want 90, 95, or 99%. If that's the case, we know the numbers. We could use 1.64 Z star for 90%, 1.96 for 95%, and 2.57 for 99%. If you don't know it, remember you can find it by taking the confidence level you want, cut it in half, add 0.5, and do inverse norm in the calculator, and it'll give you the Z star that you need. So we've talked about that before. Use the Z star that goes out for a certain level of confidence, and then you need your standard error. Standard error is that formula that I calculated, or I showed you, and I will calculate in the example. Once you've built, there's the plus and minus, once you've built the upper limit and the lower limit, you now have a confidence interval of what you think the true difference in the proportions are. So let's look at an example. So here's a great one. How much people like One Direction? Once again, I think my examples are getting old, but One Direction's still around. It's probably not surprising that girls are a little more into One Direction than guys, and this sample seems to show that. So in a random survey given about One Direction, they ask a whole bunch of young boys and girls, probably middle schoolers or high schoolers. It doesn't really matter, but what we find out is that 248 boys are asked if they like One Direction's music. 57% of them say yes. Then they ask 256 girls. So notice they don't have to ask the same amount. They asked a little larger sample of girls, and the girls came in at 70%. So there's a difference. It seems that girls, at least in the sample, girls definitely have a higher rate of liking One Direction The difference between the samples, if you subtract the boys from the girls, is a 13% difference. But once again, that's our sample difference. So the samples seem to show that girls like One Direction at a rate 13% higher. But we want to know what the true gender gap may be because our sample isn't going to be dead on. It's probably not surprising that girls may like it at a higher rate, but what are the possible values for that rate, right? What could the true value be? Because even though we found 13%, 13% may not be what the actual population value is, but it should be close. So we're going to create a 95% confidence interval of what we think the true difference between the boys and the girls are. So we need a mean and we need a standard error and we need to check conditions and then we need to build that confidence interval. So I have the work on the board behind here. You've probably been looking at it up top. So I'm going to move the screen out of the way and then we'll talk through the work that's on the board behind here. So I've built the confidence interval for this. I'll explain each step here. So at the top, I decided to use p hat sub g at 70%, the g for girls. So I decided to make the sub g for girls, the sub b for boys, seemed to make sense. So our sample came in at 70%. Our sample for boys came in at 57%. To the right of that, you'll see me make the difference between them. So when we work with two proportions, we care about the difference. The difference is 70 minus 57, which is 13% or 0.13. Now, I have to check the conditions in order to use this procedure. Now, I'm going to talk through them because it would take, the board's not that big. It would take a while to write them out. So if you were doing this on AP exam, make sure you could write out all these conditions. So I'm just going to talk through them. Before I would use the procedure, I would want to make sure that a normal kind of distribution would work here. So let's talk through each condition. The independence condition is most likely met. Basically, there's no reason one boy liking One Direction would affect another boy, especially if they were randomly picked. Same thing with the girls. There's no reason one girl would affect another, especially if they're randomly picked. Also, it doesn't make sense that a boy would affect a girl or vice versa. Once again, especially if they're randomly picked, right? So because one boy likes them doesn't necessarily make other boys or other girls like them. So independence seems met here. And if this were an exam, you'd want to write that out. The random condition. Once again, they would probably tell you this in the problem. When I type these up, I don't want to type a 3-paragraph problem like they do on the actual AP exam. So we'll just assume whoever produced these samples did them randomly. They would probably give you more information where you could either trust some agency or they would just tell you usually in the problem that they're random. So I didn't say it in the problem, but we'll just assume that that's the case. The 10% condition is based on those N values. They asked 256 girls and 248 boys, and they were already saying the problem who the greater population was. We'll just assume they were asking maybe a national survey. So there's no way 256 girls is more than 10% of the population. There's no way 248 boys is more than 10% of the population. So those sample sizes should be good so long as they were for a poll of a large, like the country or the state, something large. So we'll assume that that's met. The success-fail condition, we would have to do it for each one. So we'd have to do N times P and N times Q for the girls and N times P and N times Q for the boys. Now, I didn't show that because they all come out greater than or equal to 10, but I'll talk about the calculation. So if you wanted to prove each one, you'd have to show, 0.7 times the 256. That 70% of 256 is clearly bigger than 10. And 30% of 256 is bigger than 10. So that'd be N times P for the girls and N times Q for the girls. both of them are going to come out bigger than 10. Same thing for the boys. The boy number is a little smaller, but 57% or 0.57 times the 248, that would be n times p. And 248 times 0.43, that'd be n times q. Those will also be larger than 10. So pretty much you have to show all four of those calculations. So n times p and n times q for the boys and for the girls. Basically, you do four calculations, show what those numbers are. All those numbers will be greater than or equal to 10. So we've checked all four conditions now. Independence was met, randomness was met, 10% condition was met, and success-fail condition was met for all the groups. So it says up top here, I already assumed it because I knew it was going to happen. It says check the conditions, and now since they're met, we'll make a 2-proportion z-interval for what the true difference is. Our sample difference is 13%, but what is the range for the true value of the difference? So it's probably near 13%, but it's not exactly 13% probably. So we're looking for a range that might contain that true value. So now that I checked the conditions, then I went ahead and did the standard error. Probably should have checked the conditions before I did any of the top stuff, but the standard error formula, I would need P1, Q1 over N1 and P2, Q2 over N2. Hopefully you can read that. I did PG, QG over NG. So I took all the girl numbers, and then PB, QB over NB. Those are all the boy numbers. Threw them into that formula. So you can see here, they're all thrown in. And I got my standard error because I used, I guess technically those should be hats on there. Well, I was going to fix them, but I can't find my marker. Well, anyway, those should be the hats in that formula for the standard error. So that should be hat, hat, and hat, hat. So those are the hat values because they're the estimates. When I calculated all that, it became 0.0425. So that's the standard error. Now that we have our difference with the hats and our standard error with the hats, we can make the confidence interval. So this is at 95%. That's what it said to do. So the confidence interval at 95% would start with the difference between girls and boys. That was 13%. That's our sample difference. To make a range for the true difference, we use Z star. Since we're at 95%, the Z star comes out as that classic 1.96. And then we multiply times the standard error. So this tells us the standard, basically the standard deviation, and then how many standard deviations go out from our sample value, just like we always did. I threw that into a calculator. Remember, there's a plus minus, so you get two numbers. So the lower number is 0.0467. The upper number is 0.2133. So what this tells us is even though our sample has a difference of 13%, what is a confidence interval for the true difference? The true difference could range anywhere from 0.0467 or about 4.67, 4.6%, up to 21.33% or 0.2133. So even though our difference is at 13%, it's very possible the true difference is anywhere from about 4% to 21%. Notice that what we can garner from this is that they're both positive numbers. If they came out negative, it would actually mean the boys liked them more than the girls. Both numbers are positive, so it's indicative of the difference between girls and boys is at least 4% and can go all the way up to 21%. The real value is in there somewhere, once again with 95% confidence. So if we took samples of this size over and over and over again, 95% of the time our confidence interval would capture the true difference. So we don't know the true difference. This confidence interval also has a chance it could be wrong, but this procedure will work most of the time. So with 95% confidence, we're pretty sure that the true difference in how much, the difference between girls liking and boys liking One Direction is anywhere from around 4% to 21%. Them both being positive seems to point to the fact that even if it's the low end, it's only around the 4.6%. It seems indicative that there is at least a difference in the positive direction for girls, that girls like One Direction at a higher rate than boys, because even at the low end, they're liking them at 4% more, and they could like them as much as 21% more. So once again, we don't know the true difference of the population value, but we create a confidence interval for it. So we're 95% sure that true difference is from about 4.6% to 21.3%. And if there was a negative value in this, because we're doing girls minus boys, if the lower value maybe was negative, we would interpret that as the other way, that boys actually liking it more than girls. That didn't happen in this case. So no matter what happens, we seem to think that girls are liking One Direction at a higher rate than boys, though we're not exactly sure what that rate is. And there's no number that's more likely in here. We were pretty sure the number's in here. We don't know exactly where, but that we expect that the true value's in there somewhere. All right. Here's one. Normally in class I'd give you one to try. So I'll put this up, and because I obviously not running an actual class, can't walk around and see if people know what they're doing. I'll give you the answer. If people really want, I could show it, but overall I think if you get the other example, you should be able to come up with this. In this example, they take, once again, two proportions. This time it's New Yorkers and Ohioans. I didn't make that up. That's really what they're called. So they take a poll of 4,208 New Yorkers and 2,763 Ohioans about their seatbelt usage. Now, this one's a little different because they say 2,777 in New York wore belts and 1,363 in Ohio wore belts. So if you want to try this yourself to come up with it, you would need to come up with the proportions. They didn't give you the p hat for New Yorkers or the p hat for Ohioans, but what you can do is you can divide. If you took 2,777 and divide by 4,208, you'd get the p hat for New Yorkers. And if you take the 1363 divided by the 2763, you'll get the p hat for people in Ohio. From there, you should be able to follow my example, and once you have the p hats, you can subtract them to find the difference in the samples, use the standard error, and then use the overall formula to come up with a 95% confidence interval. Now, I told you I would give you the answer so you could see if you did it correctly. Keep in mind when you're doing these, it depends on how much you round it. I have a program that can come up with the confidence interval, so it's probably going to be a little more exact than what you would calculate. But so long as it's close, you're doing it right. Let me get this thing to generate it. So if you try this and you want to see if you know what you're doing, the confidence interval comes out 14.313% on the low end and 19.013% on the high end. So roughly 14.3% to 19%. So how do we interpret this? Well, in the problem, I didn't, I'm going to have you try it. There's a difference between their proportions. The difference of the proportions in the sample may not be the true difference, but we have a true difference of 14% to about 19%, according to the confidence interval. We're 95% confident about that. So what that tells us is that whatever the sample difference was, we're 95% confident that the true difference, and this was New Yorkers were using them at the higher rate. So I did New Yorkers minus Ohioans, because New Yorkers are obviously better. So if you do New Yorkers minus Ohioans, we believe that New Yorkers use seatbelts at least at a rate of 14.3% more, up to a rate of 19% more. Once again, we could be wrong, but 95% confidence says that if we kept taking samples of this type over and over and over again and made confidence intervals out of them, we would get the true value in that confidence interval 95% of the time. So we're pretty likely that this range of 14% to 19% for the difference is true, which tells us that New Yorkers seem to use seatbelts at a higher rate, somewhere in the teens, so double-digit percents there. So we're using them at a significantly higher rate according to this. So hopefully you try that and you come up with the same numbers I did. There'll be more practice problems that I'll give you. Sorry, this one's a little long, but the procedure takes a while to go through. So that should be all on confidence intervals for two proportions. Next, we'll do the hypothesis test for two proportions. Between that will be everything we do for proportions. So just going forward in class, we did one proportion interval and a one proportion test. This is the two proportion interval. The next lesson will be the two proportion test, and then you know everything about proportions. And then we have another set to do of inference that's on means. So we'll get through, try to make videos on all that. And, oh, there goes the computer. So be on the lookout for that. All right.